All right, I'm Keep, and this is PCBIC. In the previous three episodes, we talked about the main K return path. A lot of people think they get it at this point and feel like RF isn't that hard. Don't celebrate too soon. What we're covering today is the real nightmare for RF engineers, and these things are especially well hidden. If you look at RF design, today we're going to reveal five hidden issues. Sneaky via capacitance and skin effect, cutoff loss, and roughness of copper traces. Normally, you can hardly see them, but they secretly eat away at your performance. What's frustrating is that the PCB won't give you any error messages. In any case, you probably won't get any warnings until you start testing and the VNA begins to teach you a lesson. A lot of people think vias are just holes for passing signals, but for RF engineers, the first thing that comes to mind is inductance, because as soon as current flows through, it has to complete a return path, and that return path creates higher inductance. The problem becomes more obvious. So there's a saying among RF engineers: every via quietly adds a bit of trouble for you. It might not seem like much, but when there are enough of them, they'll gang up and cause you real issues. Digital engineers like things big. Big traces give them a sense of security, but when RF engineers see a big pad, they often get nervous because underneath, the ground plane naturally forms a. The larger the area of the pad, the greater the capacitance. Don't underestimate the impact of this at certain frequencies. It can totally throw things off. So, when it comes to pad design in RF, the rule is simple: just make it big enough, don't overdo it. A lot of people think current flows evenly through the entire copper trace. At low frequencies, that's true. But at high frequencies, current starts to get picky. It stops flowing through the middle and only travels along the surface. That's the skin effect. The higher the frequency, the more the current sticks to the surface, making the effective area smaller, which means resistance increases. And that leads to more loss. To put it simply, take the same wire as an example. The higher the frequency, the more it gets secretly eaten away. If copper eats up power, then the molecules in the PCB material will also go wild with the electric field. At low frequencies, it can still keep up, but once the frequency goes up, it starts to lose sync, so some of the energy turns into heat. This is dielectric loss. That's why FR4 is fine for Bluetooth, but for millimeter wave applications, it might not be acceptable. This is also why many high frequency products are willing to pay a premium for higher grade dielectrics, not just for the brand, but for lower loss. Just now, we mentioned that high frequency currents prefer to travel along the surface, and here's where the problem comes in. If the surface itself is rough, imagine a highway turning into a mountain road, even if the distance is the same. With all the twists and turns, the actual path gets longer, so naturally the loss increases. This is the issue with copper surface roughness. The higher the frequency, the more obvious the impact. That's why a lot of high end RF boards are very particular about the copper foil they use, because every little bit of loss really matters. So, what happens when all five bosses show up at once? A single issue on its own might not feel like much, but the scariest thing about RF is when problems gang up together. Add a little inductance from a via, a bit of loss from electroplated copper, and in the end, the result is worse performance, increased loss, lower efficiency, and higher noise in the field. Then you start to wonder if the chip is broken, but actually, the chip is just fine. After these 4 episodes, we finally pieced together the core framework of FPCB. In the first episode, we talked about how RF and digital PCB are fundamentally different ways of thinking. The second episode was about impedance, the third about return paths and reference grounds, and the fourth about parasitics and crosstalk. You'll realize that all these issues are actually interconnected. Return paths affect impedance, which in turn affects reflections. Parasitics affect matching, losses affect efficiency. Truly outstanding RF design is never just about luck. It's about careful measurement, thorough validation, and constant repetition. Thanks for watching.